Alright, now we don't have a lot of days. Here's all the outcomes that I'm supposed to cover. Okay? I realized yesterday, I never realized this before actually, that there are actually two separate units. But the first one, magnetic fields, is basically like a day and a half. There really isn't a whole lot in it. So I combined these. Actually, they used to be together with electric fields, and that was way too much. Okay? And generally what I found in the last few years is that I don't really get very far into magnetic fields. But it is another opportunity to sort of get some easy marks on the exam. So you're supposed to be able to define the magnetic field as the region of space around a magnet where another magnet will experience force. In other words, know the definition of a magnetic field. I already gave it to you. I pretty much covered it already. Demonstrate and diagram magnetic fields using lines of force, include bar magnet, horseshoe magnet, between like poles and between like poles. Very, very similar to drawing electric field lines. Almost identical. So you'll have no problem with that. Those are easy. Describe the concept of magnetic poles and demonstrate that like poles repel and unlike poles attract. You probably know that already. North and south attract, right? Describe magnetism using the domain theory. That's a bit of a challenge. We won't get to that for another day or something. Investigate the influence and effects of the magnetic field of the Earth, include auroras, magnetic declination, and inclination. Auroras, we all know. What are those? You see it in the northern lights. Okay? Northern lights. Magnetic declination and inclination I will talk about on Wednesday. It's my patented explorers go and spend the entire winter in the north lecture. And that's it. I can cover all that in very little time. Okay, now electromagnetism, we won't get to all of this. Okay, but this is what we're supposed to cover. Describe and demonstrate phenomenon of electromagnetism. Diagram and describe qualitatively the magnetic field around a current carrying wire, direction, intensity. Diagram, blah, blah, blah. I will not perform a lab. We will not be doing that. I may get to this right here.
Oh my God.
Okay, we'll see how far I get. I will clearly outline for you on probably the Monday exactly what we've covered under magnets, and I'll leave it like that. Paul, what's up? What you doing, man? Pardon me? Great idea. Okay, on the back side, a little sort of introductory little article, which I'll just quickly go through with you. How many people have ever had an MRI? Have you? I've had an MRI on my head and on my knee. You guys too? What does MRI stand for? Magnetic resonance imaging. Magnetic resonance imaging. Now, what does it see? Like, what's the difference between an MRI and an X-ray? Yeah. It does. What does an X-ray see? X-ray sees bones, and the MRI sees more soft tissue. More soft tissue. Exactly. Now, what did you have your MRI on there? On your foot? Okay, so they put you into the tube thingy, right? So in the tube thingy, it's basically a giant magnetic field. I'm guessing for a foot, you probably didn't go up much past maybe your knees or your waist. Yeah. For my knee, I went up to my waist. For my head, I had to go like all the way in, like 20 minutes. Kind of claustrophobic, right? Actually, when I had the one in Brandon, was it Brandon, I think? In Brandon, they asked me, do you want some music? I was like, sure. And so what channel? So they gave me headphones, and I just basically relaxed, and I think actually I fell asleep. I've done that too. Your mouth open? Why?
Yeah.
Concussion.
Let's get an MRI for concussion.
Yeah. They found I had no brain. How they get no brain? That's my life. Surprisingly, I'm actually a good skater. And I was going a little fast, and I bounced off of the fence, and I saw my butt.
That's psychological.
Okay, so a little argument. Now, when you get your MRI, there's a big warning sign up there that says, do you have any metal in your eyes? Do you have any pins in your body? All that stuff. How come? You're going into a giant magnetic field. If you're welding or something, or machine, you can get little flecks of metal. Tattoos as well, because Tattoo ink is actually metallic, and if you've got a tattoo, it can cause a problem. Let me read you the article. When a 6-year-old New York boy died after a metal oxygen tank flew across the hospital room toward the giant magnet at the core of the MRI scanning his brain. Why are you laughing?
That's insane, though.
Well, it happened. This is from 2004. David Holt realized that something needs to be done. Accidents that damage equipment or cause minor injuries are not uncommon when staff forget to remove pages from their belts or fridge magnets from their pockets. Yeah. Who has a fridge magnet in their pocket?
I do.
Never know.
But Holt, a principal research officer with the National Research Council in Winnipeg, said it took depth to galvanize the research community. He has built a prototype detector for the entrance to the magnetic resonance imaging suites that's so sensitive it keeps the door to the scanner firmly locked if someone walks to the detector wearing a bottle kit. So it's locked unless you are completely metal-free. The prototype, which took 3 years to develop, looks like the airport metal detectors that passengers have to walk through, but it picks up only magnetic materials. Iron, steel, and magnets can turn into fast-moving projectiles in an MRI suite, but silver, gold, copper, and brass are safe. When Holt steps to the detector wearing his belt, it sounds a loud alarm, but it raises no objection to his brass zipper. Holt is negotiating with a U.S. company that wants to manufacture the detector while paying a licensing fee to the government-funded agency. The potential market might include hundreds of research hospitals in the United States. I mean, think about how many MRIs there are, right? And at the cost at about $40,000 US for a detector that can prevent damage to MRI machines worth millions of dollars. Pretty good company for him to invest in, right? That's an enormous investment to have an accident. Most patients wear only hospital gowns into the MRI suite, but they may have implants in their bodies of which they're not aware of. In one case, an aneurysm clip twisted inside someone's body to align itself with the magnet, breaking the blood vessel, and would have caused a problem in their brain, right? Holt is still working on improvements that would allow his invention to detect the minute clips. Staff are the biggest safety risk because they are fully clothed and sometimes forget the rules. Holt said he didn't realize that magnetic coins were magnetic when he first came to this country from the U.S. Had a new job in Ottawa, they shot out of my pocket straight into the magnet. U.S. coins, not magnetic. Fortunately, no patient was in the MRI. Spokeswoman for the Winnipeg Regional Health Authority said there have been no mishaps here with the MRI machines. Patients in Winnipeg are questioned extensively, and I do remember it was like about a 2-page questionnaire when I had mine, even about their work history, since welders can have metal particles in their skin. Holt's invention takes advantage of the low-level magnetic fields near MRIs, which magnetize metal in the area. When magnetized metal passes between coils and the detector, it generates a voltage that sets off the alarm. Holt said the biggest challenge was finding a way to prevent the vibration of the National Research Council steel frame building on Alice Avenue from setting off the alarm. So it's a scientific process, scientific sort of phenomenon, you might say, that when you've got metal passing through the coils of the detector, it generates a voltage. When you've got, a hand crank where you generate the light, okay, you're turning copper wire, copper coil inside a magnetic field, and that's what generates electricity. Who's got a generator at home? Gas generator. Lots of people, right? How does it work? Gas motor turns a big thingy, right? It's copper wire in a magnetic field, generates electricity. That's how they detect the metal here, because the metal in the coil will generate electricity and will set off the signal. So, a use for magnetic fields. Okay. What order should we do this? Let's do the magnetic flip-flop one, then we'll do the quiz. Let's do this one next. Okay? Earth's magnetic flip-flops. Now, you might think that I'm talking about some sort of flip-flop, some sort of shoe that stays stuck to your ground, or stays stuck to your foot with magnets, but that's not true. Which way is north, Dave? Point north. Which way is north? Not up. That way's north, right? Actually, we're kind of turned a little bit. No, we're not. North is kind of that way, right? It's been a while since I've talked about magnetic inclination. Well, did you know that the Earth's magnetic field changes? Did you know that? Let's just zoom in a little bit here. Yeah, now that you know? Okay, so this was from 2004 as well. Do you guys know where the Mid-Atlantic Ridge is?
No.
I'll give you a hint. It's in the middle of the Atlantic, hence the name. So, next time Earth's magnetic field flips, compass needles will point south instead of north. What? Scientists can't say when it will occur, and until now they've disagreed on how long the transitions take. A new study pins down how long it took for the last 4 reversals to play out. It also finds that the dramatic turnarounds occur more quickly near the equator than at higher latitudes closer to the poles. That means that folks living during the next reversal, which some scientists speculate might be underway right now, we see compasses change and behave differently in different locations, said study leader Brad Clement of Florida International University. So when you get out your little compass thingy, it points north because that's the direction of the Earth's magnetic field. But they think that the Earth's magnetic field is changing and that compasses are actually going to end up pointing south. Why is it changing? They don't really know. But all I can tell you is I can show you the evidence that points towards that happening, which kind of means that it's likely to happen again. But they don't really have a firm understanding of what. Okay, so let's just talk about this a little bit. So, Earth's magnetic field is thought to be generated deep inside the planet. An inner core of solid iron is surrounded by an outer core of molten iron. I'm just going to make that a bit bigger for my, oops, my poor little eyes here. Let's go 150%. That's better, okay. Earth's magnetic field is thought to be generated deep inside the planet. An inner core of solid iron is surrounded by an outer core of molten iron. They rotate at different rates, and the interaction between the region creates what scientists call a hydromagnetic dynamo. I don't even know what that means. It's something like an electric motor, and it generates a magnetic field akin to a giant bar magnet. The process is not completely understood. In fact, one study suggests the planet's mantle, which surrounds the core, also plays a role. However it works, the setup has been in place for at least 3 billion of Earth's 4.6 billion years. Science figure. But the field is shifty, periodically growing stronger and weaker, moving around and even flipping its polarity entirely. In the past 15 million years, there have been 4 reversals every 1 million years, or about one shift, each 250,000 years. The last one, however, was 790,000 years ago. That might suggest that we're overdue for a big change. Likely. But not necessarily so, coincidence. The flips are not periodic, meaning they don't adhere to a schedule of even intervals. So some years it might be 250,000, some years. Sometimes it might be 250,000, sometimes it might be 790,000, right? Quite likely, though, we are likely in the process of flipping it. Now, does that mean tomorrow we're all going to wake up and birds are going to fly north? No. Doesn't mean that. The intensity of the magnetic field has been dropping for the last 2,000 years. And it has dropped significantly during the past 2 decades. And in fact, this article is 10 years old, and it's likely dropped even more so since. The Earth's magnetic field is, and here's the nerd me coming out, 5.0 times 10 to the minus 5 Teslas. Just one of those random numbers that I have memorized. Tesla is the unit of magnetic field strength. You know Nikolai Tesla? Tesla Motors, anyone? Anyone know what a Tesla motor car is? Anyone ever hear of Thomas Edison? Hands up if you heard of Thomas Edison. Yeah, everyone loved Edison. Turns out Tesla and Edison, they were like battling. They were like, they were battling. Okay? Edison was the guy that everyone remembers. He won the battle, but it turns out that Tesla was probably the one that should have won the battle. Tesla was an amazing inventor. Edison was
a good stealer.
I'll let you look it up for yourself. But there is quite a lot of controversy behind Tesla and Edison. There's a guy in Tesla's workshop in somewhere in the New York region was going to be torn down. This one guy, he's such a huge fan of the Tesla history that he bought the building, wants to turn it into a Tesla museum, crowdsourced the money to buy it so that he can have this monument to Tesla, because he's sort of like the forgotten scientist kind of thing. Although he does have a unit named after him, magnetic field strength. Who's seen the movie with the 2 magicians? They clone each other. I don't want to give away the ending. Anyone know that movie? What's it called? The something. No, it's like about 10 or 12 years old. Christian Bale in it, I think. No one?
Oh, must be good.
David Bowie. Yeah, it's actually a good movie. David Bowie played Nikolai Tesla. All fiction, but kind of an interesting movie.
The guy played Nikolai. Oh, Nikolai was the guy.
Yeah, Nikolai was a guy.
Oh, wow.
Yeah.
It's Nikolai, not Nikolai.
Nikolai Tesla, Russian.
Well, he's a Tesla for a while. So
Yeah.
Oh,
Okay, so some scientists speculate that a reversal is underway. Clement said that's like forecasting that the bottom will drop out of the stock market. because it's gone down the past few days. We just don't know, he said. Researchers also have not known how long it takes for the magnetic field to make a transition. Studies have, and now I've got some problem here, right? Studies have suggested anywhere from 1,000 to 28,000 years are required to initiate and complete a reversal. I'm on the back side of the paper now. It's generally accepted that during a reversal, the geomagnetic field decreases to about 10% of its full polarity value. After the field is weakened, the directions undergo a nearly 180-degree change, and then the field strengthens in the opposite polarity region. So it decreases in strength, makes the flip, and then increases again. How do they know this is happening? I'm going to explain right away. A major uncertainty, however, has remained regarding how long this process takes. Clement examined sediment cores gathered from deep ocean sites in a National Science Foundation program. The cores provided readings at multiple sites for the past 4 flips. He found that each took about 7,000 years. I'm going to draw a picture right away. So what they've done is they've taken sediment cores there, they've sent down drillers, they pulled out rock out of the Earth's core, out of the mantle, and then they've studied that. It takes less time, about 5,000 years, for the reversal to occur at lower latitudes, closer to the equator. And it takes longer, about 10,000, for the flip to play out near the poles. So not only would compasses... Not only would compasses gradually do a somersault readings, but Arctic dwellers would see changes that wouldn't match what tropical observers would note across a generation. So we may well be into a period where people are not going to be able to use compasses. Nobody understands how the shift occurs. Perhaps, Clement says, magnetic field shrinks to essentially nothing, leaving several mini poles at the surface before the main poles revealed on opposite sides of the world. Scientists have plenty of reasons to seek a better understanding. For one, the magnetic field's line extend out beyond Earth's atmosphere and provide the first line of defense against strong solar storms. That answers the question, why do we even care about this? Earth's magnetic field is literally a force field that keeps radiation away from civilization. Okay? It's a giant defense system kind of thing.
What's radiation comes from?
Where does radiation come from?
Besides bombs.
It comes from the sun.
Okay.
Yeah, the sun is a huge source of radiation. Yeah, in fact, astronauts come back, they've been exposed to long-term radiation because they're not inside the Earth's magnetic field and they don't have that defense. So yeah.
You ever seen the show The 100?
I have. It was kind of bad, actually. I watched 3 episodes, then we gave it up.
They talk about radiation.
That makes it good?
Yeah.
Okay. That's actually one of the problems with long-term space travel is they don't know how to keep people safe from the radiation.
Exactly. So
Yeah.
used to it, so they come back here, they're like, boom.
Okay, and I know they're Spider-Man, right?
Yeah.
Exactly. Okay, Clement wonders how the reversals might affect navigation by migrating birds and other animals that key in on the magnetic field to find their way. 7,000 years is probably enough for them to adapt. Clement has demonstrated that magnetic field reversal events occur within certain time frames, regardless of the polarity of the reversal, said Carolyn Ruppel, Program Director of the National Science Foundation's Division of Ocean Sciences. Blah, 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 blah. Let's look at this picture right here, because this is the one you need to know.
Why don't you give us these favors and you can just look at the screen?
So you can look at it later?
You're pretty much with Robert so far.
Fair enough. Here's how they know, okay? Down the middle of the Atlantic, there is what is known as the Mid-Atlantic Ridge. And basically what it is giant, a ridge of volcanoes all the way down the middle of the Atlantic. There's this giant ridge of volcanoes. And it sort of looks like this. And here's the ridge right here. Okay, what's underneath? Magma. What's magma?
So it's not like a trench or anything.
No, it's a ridge. It's like a giant mountain range down the middle of the ocean.
It's not called lava until it's over.
It's not called, everyone knows that for some reason. It's called lava once it reaches the Earth's surface. It's called magma when it's below, right?
Some people didn't, they were saying it was lava.
Oh, was that right? Magma is molten rock below the Earth's surface. It's very soft. Okay? Generally, it has a strong iron component. Iron can be magnetized. So when the soft, malleable, very sort of loosey-goosey magma comes up, what it does is it aligns itself, it becomes magnetized, but in the Earth's magnetic field. So it creates a giant bar magnet. You see that white stripe right there? creates a giant bar magnet that points north one way, the one end is north, and the one end is south. But because of this reversal, right, they'll find on the next strip, they'll find that this end is south and this end is north. And then they'll find on this one it's north and then south. They can literally see the stripes on the ocean floor. Okay? Can they actually like see them like this? No. They have to actually test to see how the magnetic direction of it, right?
Divers like went down there like.
Yeah. Yeah. Now, because of this magma, see these arrows over here? Okay, you guys know about like plate tectonics and stuff like that? What does that mean? What's plate tectonics? Yeah, like the whole globe, right? The whole globe is made up kind of like a giant jigsaw puzzle, right?
Where's the
Yeah.
church on your
That's how Ken J.
Right down the middle of the night it goes.
Oh, it's one of those ones that has like it's all raised when it's higher.
Yeah, there are some like that. Yeah. So the North American plate or the North American jigsaw puzzle is over here, and the European one is over here. Because of this plate tectonics, those plates are moving one to the right, one to the east, and one to the west. And so where does this lava go? It sort of spews out, and it cools off. And when it cools off, that magnetic field remains sort of like frozen, stuck. And that's how they can tell. They see these stripes. And it's actually traveling about, I think it's like about 3 centimeters per year. Okay, every year you get about 3 centimeters more of a stripe. Are all these stripes equal sized?
No.
Are they like nice, straight, perfect lines? No, it's all sort of messy, right? But overall, they can tell, and that's how they know when all these reversals have happened, because they know that the plates are moving apart about 3 centimeters a year, and they measure how wide that stripe is, right? And then they can just do a little simple math and tell you how long it'll happen.
That adds up.
Does that kind of make sense? Yeah?
Where's Mariana's Trench on here?
Pacific Ocean, I think. Could be wrong.
Look, it's a label.
It's not called a northern spectrum.
Okay.
That's a good way.
You should have on your third sheet, you should have the true and false questions. There are 9 of them. Please enter your answer through the clickers, and then we'll go through them and we will see what you know before we begin the unit. Alrighty, so it looks like everyone has completed, so let's just see how you did. See what you know. I'm not recording this. This is strictly what do you know about magnets? What do I need to do to cover some of the misconceptions? Okay?
Oh, 88%.
Some of you may have taken an opportunity to check your phone. It's now time to refocus on me and listen. So, this is the first where objects are attracted or repelled to each other. Obviously, the answer is, yeah, I gave you an easy one to begin with. C, magnetism. Magnets have a north-seeking pole and a south-seeking pole. Correct answer? True. When we say north-seeking, what that means is that end of the magnet points towards north. Now, I have a question for you. If you were to go to Santa's workshop, and there isn't, by the way. There might be Santa's workshop. I'm not saying that. I'm not saying any of that. What I'm saying is there isn't a big giant magnet sticking out of the snow, but if there was, would Santa have a north pole, or would he have a south pole sticking out of Santa's workshop? He would have a south pole. Why? Because the north-seeking pole seeks for geographic north, and the reason it looks for geographic north is because north is actually south.
That's the biggest plot twist.
Yep. I'm surprised that's not an M. Night Shyamalan movie. Glad someone gets that. 2 of the same kinds of poles repel each other. True. I don't know, someone got it wrong. True that. 2 opposite poles attract each other.
Okay, I want to know something. How can you get the other one wrong and get this one right?
The world is a mysterious place, Lucas.
That's what I did.
The area around a magnet that behaves like a magnet is a magnetic. It's really the name of the unit. It's a magnetic field. Please tell me everyone got it right?
Yay.
Magnetic field. So what that means is that the area around, right? Because here's the Earth. The Earth basically has a giant magnet in it, and the area around it is magnetic. A magnetic field. It behaves like a magnet. That's why your compass points north. The further apart two magnets are from one another, the stronger the forces that attract or repel them. How'd you do? It's not stronger, it's weaker. And once again, it's the inverse square. Inverse square rule, twice as far. No, inverse square, twice as far. 4 times as weak. Like sound, like light, like electric field strength, magnetic field strength, pretty much everything inverse square, if it's 3-dimensional. When magnets are broken into small bits, the bits themselves can become small magnets. True. If you take a regular bar magnet and you break it, like so, here's what you end up with.
When you cut a worm in half, you get two worms.
Yep. That's what you end up with. There is a north end to the South Pole, okay? And this is the whole idea about domain theory. And I'll just briefly touch on this. Domain theory is this. How many people have done the chemistry bit yet where you hear about the electrons and how they spin? And you know that one spins this way and one spins this way. Does anyone know that yet? I think you're right. I think it is a big call. Did I tell you that already? Okay, so the electrons spin in opposite directions. When you've got an unpaired electron, like in iron, is iron magnetic, Jake? You must be looking it up. Is iron magnetic? It is. How come? It's got a single unpaired electron. And so all of these chunks of iron, what happens is the single unpaired electrons start spinning in the same direction, and it all lines up. And when it all lines up, you've got yourself a magnet. I was going to write magnetic. You've got yourself a magnet. When all the domains, when all the electrons start lining up, now you're finally quiet.
There you go. At least I found someone to keep you quiet.
Yeah, but you're not listening anymore.
So what?
Naturally occurring magnets in nature are called... Ooh, I haven't given you this one yet, have I?
Got that one right. Yep.
Did you? Yes, they're called lodestones. Anybody get that right? Lodestones. I have some back there. I'll pass them around a bit. It's basically a hunk of rock that's magnetic, generally from a volcanic region. I had high hopes when I was in Greece a few years back. We visited an active volcano. There were these little rocks lying around, and one, shall we say, inadvertently got lodged in my pocket. And it inadvertently came home.
Really?
You have it?
Would
Would you steal?
Totally an accident.
You great class.
I think so. I think I don't know because I looked at it. I could see that it was. I knew it was from a volcano. I could see rust on there. I could see the iron oxide. I thought that's got to be magnetic. It turned out it wasn't. Very disappointing. Extremely disappointing. I think I should go back and return it.
Go for it. This one doesn't work.
Yeah, exactly. Yeah. It probably does have a magnetic field. It's just very, very, very weak.
Wait, what? I got that right.
Which of these is not needed to create a simple electromagnet?
Oh.
Yeah. Okay, if you've got a battery, copper wire, and a nail, you can turn the nail into electromagnet. What does electromagnet mean? It means it's only a magnet when
Electricity.
the electricity's on, right? So you got your battery, right? And you got your wire, and then it's curled around a nail like that, right? And then the nail becomes a magnet. Are these useful for anything? Absolutely. They're in almost everyone's home.
That's like if you
They're in your car.
Mr. Bennett,
No.
that's like if you strike a what's it called?
Yeah.
Mortars, that's like a fever flame.
Yeah. Comes back, yeah, exactly. They're called a solenoid. It's in your car. It helps to start it. It's in your doorbell at home. If you take the cover off your doorbell, you will likely see a coil of wire. It creates a magnetic field, and it turns that iron bar into a magnet, and that's what turns or pushes it into the bell. Oh, I have something.